All right, so we've been talking about intermolecular forces. We've been talking about solubility. We've been talking about different properties like melting point, boiling point that change based on intermolecular forces, wetting, viscosity, right? Lots of different things. So here's something that, again, we probably already know, but we want to kind of remind ourselves of. If we go from a liquid to a gas, if I take a system that is a liquid water, let's say, and I want it to be a gas, I have to put energy into that system, right? And why is it?
Well, you're, like it says on the slide here, overcoming those intermolecular forces.
That's right. You're overcoming those intermolecular forces. You're convincing the molecules, which we'll just draw as spheres here, clustered together in a liquid form. You're trying to make it go to a gaseous form. So all of these spheres no longer are being bound together by intermolecular forces because you've added enough energy to get them to separate. When they hit now, they hit with so much energy that they bounce right off, and that's the way gases behave. If you remove the motion, lower the temperature, right, then when they hit, those intermolecular forces will be strong enough to keep them in a liquid form. And if you continue to lower the temperature, then you would actually get into a very ordered solid form, right? And that's the difference between a liquid and a solid. Solid is very ordered, right? Usually coming into the form of a lattice of some sort. Liquid is disordered, and gas, all the molecules are completely separate from each other. Now, when liquid goes to gas, right, evaporation, that is an endothermic process. It requires heat energy for liquid to go to gas. So, if I have some liquid on my arm and something happens to make that liquid evaporate into a gas, so I have some water on my arm and the water evaporates into gaseous water from my arm. Well, when that happens, the process is endothermic, meaning it is requiring heat from the surroundings. All right? Now, my arm provided some of that heat, and so the result is, and this is what happens if you put a little bit of water on your arm and you blow across it, those water molecules begin to evaporate, get blown off, and it leaves your arm feeling cool in that spot because as the evaporation occurred, it required endothermic. It took in heat from the surroundings. And if the surroundings happen to be your arm will feel cooled down.
Is that why we sweat?
That's right. That's why we sweat. So when we have sweat, when our body is hot, it will secrete water, and that water, as it gets blown off of our body, cools us down. The evaporative process cools us down. That's also why if you are having heat stroke, where you don't have enough water in you, and your body tries to sweat, but there's not enough water, so it won't let out any sweat, your body can't cool itself down very well. So people who have heat stroke, who aren't drinking enough liquids, the reason why they can't cool their body down is because water is not being released from their body. They're not sweating. It's also the reason why if you have a fan blowing on your face all day long and your face gets dried out, then after a while it doesn't feel like the fan is cooling you down, because just blowing air across your face will not cool you down. You need to have some water to evaporate away. Another very, well, I don't know, doctors will tell you to be careful with this, and it's a good idea to be careful. But oftentimes, when little children have really high fevers and they need to be cooled down really fast because it could be dangerous for them, something you can do is rub their back with a little bit of water, right? And that water evaporating off of their back will cool them down. And because rubbing alcohol has fewer intermolecular forces, if you put just a little layer of rubbing alcohol on their backs and then let that evaporate away, it'll evaporate much faster, and so it will remove the heat faster. Now, this can also cool down somebody really, really fast, and so doctors want you to be really careful if you do that. But I've always done that with my children. If they had a bad fever, we use a little bit of rubbing alcohol, rub it on their back, and then fan their back, and that cools them down really quick. And keeping their temperature below 102, 103 degrees is important for their health, right? Above 104, you start getting permanent damage in some cases, and that's why they tell you to bring it to the doctor so they can help you cool it down, the child or a person. Okay, so you see these endothermic processes. Any process going from solid to liquid or liquid to gas or even solid right to gas, any process that has to overcome those intermolecular forces requires energy to be put in. On the other hand, when something condenses or something fuses liquid to solid or deposits gas to solid, those processes are exothermic. That means they're releasing the energy that they had in the form of forming those intermolecular bonds, right? They form bonds, intermolecular, not intermolecular, and they're not really bonds either, they're interactions. But those interactions will release energy as they form. All right. Now, just a reminder, the relationship between temperature and the boiling point, right? This minimum escape kinetic energy, for example, is the energy necessary to convert the molecules in from liquid to gas. And if you raise the temperature of a system, what you do is you shift more of the molecules towards the evaporative zone. And again, what this is showing is that not all of the molecules will just all of a sudden jump off, but some will have enough energy to jump off. Okay? And what this is letting us know is that this changes of state that is occurring is in equilibrium between the condensed phase and a separated phase, whether it be solid to liquid or liquid to gas. All right? So for example, if I have a container with a liquid in it, and I allow the molecule inside this box, which is sealed. All right? This box is on the surface of this table. I have a container of liquid in this table. I'm going to have evaporation occurring, but those molecules aren't going to go anywhere. They're just going to they're not going to go anywhere. They can't go very far. And so as a molecule is lifting off the surface, now I like to draw this because it helps us to kind of imagine this. Here I have a bunch of molecules, right? They're all on the surface. So here's my container. These are exaggerated in size, obviously. And here is one molecule, the rebellious molecule, teenage molecule, wants to leave its family. I didn't want to get out of here. I'm so mad at this, right? So it finally gets enough energy. It's right at the end. Hooray! And it jumps off. These other molecules are trying to hold it back. They're intermolecular forces. No, don't go. Stay here, right? But as it's jumping off, it sees over here a very happy reunion, a wayward child coming back, right? Coming back and joining and thinks, oh, should I have not left? That one left, and now it's coming back. And this is going to happen in an equilibrium. You're going to have evaporation and condensation occurring in a fixed container like this. All right? So this here is showing before equilibrium is reached, and eventually equilibrium is reached, and the rate at which they come off is the same at which they come on. It doesn't mean that they stop leaving. It just means that just as many as leave come back onto the surface. Okay, so equilibrium is reached. All right? The point at which this equilibrium is reached depends on intermolecular forces. All right? Sometimes intermolecular equilibrium will be reached when only very few molecules are floating around. Sometimes it takes a lot of molecules floating around. That means a lot leaving and a lot coming in before this equilibrium will be reached. Melting also involves this process. So going from solid to liquid, if you have some solid floating around and some liquid in a liquid of, for example, ice, if you have a piece of ice floating in water, at the same time that the ice is melting, some of the water molecules hit and stick. All right. Now, if the surrounding temperature is warm, then gradually the ice will continue to melt. But if the surrounding temperature is close to that of the ice, then you'll be, again, in equilibrium. All right. So we can get what we call a vapor pressure. The vapor is this gaseous component that evaporated from our surface. And it results in a gas inside this fixed area. And as you know, a gas inside an area results in a pressure, right? Because the gas molecules are moving around and running into the walls there. Well, the pressure that results from a liquid dissolving into a gaseous phase in a fixed container like this, or in a fixed volume and also in a fixed size, right? Or it's fixed volume, sealed. It's not going to, it's fixed volume, yes, but the molecules can't escape anywhere. Therefore, a pressure results. Now, would you get a higher pressure inside a container if there were more molecules, or would you get a higher pressure if there were fewer molecules?
More molecules, right? Because they would be hitting the walls and making a higher pressure?
That's right. So more molecules means higher pressure, and you get more molecules when you have weaker intermolecular forces. So you can look at the same temperature. Sorry, here's the same temperature right here, 70 degrees for propylene glycol, acetic acid, and water, and see that at the same temperature, water has a higher vapor pressure compared to acetic acid and propylene glycol. And that's because comparing water, acetic acid, and propylene glycol, water has the weakest intermolecular forces. It can hydrogen bond, yes, but propylene glycol can has a dipole-dipole and can have lots of London forces. Acetic acid is larger, therefore it has more London forces, and it can also hydrogen bond. All right, so given a specific temperature like 70 degrees, you can see that the one with the fewest amount of intermolecular forces is going to have a higher vapor pressure. It's going to float off, and more molecules are going to be floating around, causing the pressure. All right, now, what's the boiling point of water? I asked you this before. Do you remember what the boiling point of water is?
Yeah, I remember. It's 100 degrees Celsius.
Very good. Do you remember Fahrenheit?
Oh, I can't remember the Fahrenheit one. What is it?
212 degrees Fahrenheit. You don't have to remember that. Celsius is the most important one to remember. But now that we know the boiling point of water, I'm going to have to change your answer. Because now the answer, what's the boiling point of water, is no longer going to be 100 degrees Celsius.
Why not?
Well, because we have to have a different parameter when we ask that question. When somebody says, what's the boiling point of water, your answer has to be, well, what's the surrounding pressure, right? Because the boiling point of water changes if you're at sea level, or if you're in space, or if you're at the top of a mountain, right? The boiling point of water changes based on the surrounding pressure of the molecules of water. So to avoid this confusion, if somebody says the normal boiling point of water, or normal boiling point of a material, what they're specifying is at 1 atmosphere of pressure, which is typically what you'll have at sea level. Okay? So what's the boiling point of water?
It's 100, well, so you're saying normal boiling point or just the boiling point?
What's the boiling point?
Well, what pressure?
That's right. Very good. If I say the normal boiling point, what's that?
That's 100 degrees Celsius.
Very good. But boiling point can no longer be used willy-nilly like that. You need to say what pressure are we talking about? And that's not just for water, that's for any compound. The boiling point of a compound will change based on the surrounding pressure. And again, talking about our surface molecules that want to jump away, one of the things that's keeping them from jumping away is the atmospheric molecules. They continually collide with this surface and will force these molecules on the surface of this container back down. And that represents the atmospheric pressure. When there's fewer of those, then it's easier for the molecules to escape. But when there's more pressure, then those molecules will be pushed down. Okay, that's a good place to stop. See you next time.
Thanks a lot.
Sorry about that.
Okay, bye.